Welcome all. In this session, I'll be discussing some good quality questions on applied thermodynamics like vapor compression refrigeration system, like your Otto cycle, diesel cycle, then Brayton cycle, your Rankine cycle. All these things I'll be discussing in this session. So I'll try my level best to cover some good questions. So let us start directly. Chalo, let's take the first question. A cyclic steam power plant is to be designed for a steam temperature at a turbine inlet of 400 degrees centigrade. The steam is entering the turbine at 400 degrees centigrade and 18 bar, and the exhaust pressure is 0.08 bar. That is, the condenser pressure is 0.08 bar. After isentropic expansion, clearly it is given in the question, the expansion is isentropic. After isentropic expansion, the moisture content at the turbine exit or exhaust is not to exceed 15%. What does it mean? It means the moisture content should not be more than 15%. It clearly shows that the dryness fraction should not fall 85%. So it means the dryness fraction is given as 85%, that is 0.85. So it should not fall, because here moisture content is given, where moisture content is nothing but the wet part. It should not exceed 15%. Okay. So the dryness fraction at the turbine exit, at the most I can take, the worst case is 85%, that is 0.85. It can be more than that, no problem. Chalo. The properties of steam are given, and for superheated vapor, the enthalpy at 400 degrees centigrade, enthalpy is given. The mean temperature of heat addition. This is very good question. So he is asking the mean temperature of heat addition. Already we have seen what exactly is the mean temperature of heat addition. Let's try to understand. So this is our TS diagram, okay, and superheated steam at 18 bar and 400 degrees centigrade. This is state 1. Here the temperature is 400 degrees centigrade given, and the pressure is given as 18 bar. So this state, let me take this as 0.1. This is the entry to the turbine. And clearly he said at the exit of the turbine, the dryness fraction or the moisture content should not exceed 15%. Moisture should not be more than 15%. ठीक है, sir. Okay, right. Now, if the moisture content is increasing, the point will shift to the left. So if the dryness part, vapor part is increasing, it will shift to the right. So at the most, the dryness fraction is, look at, it cannot fall below 85%. It has to be 85 or more than that. So let us try to solve this problem with 85%. Chalo. Now, this is the condensation. Then we have pump from 3 to 4, and then it is the heat supply. The heat supply is taking place from 4 to 1. So I can write heat supply is equal to, if I apply steady flow energy equation from 4 to 1, the heat supply is given by H1 minus H4. Wonderful. Now, what is he asking? You know that when you are supplying heat, the temperature is changing. So we'll try to find out one constant temperature that gives the same heat. So this is the minimum temperature during heat supply. This is the maximum temperature. Mean will be in between. So let this be the mean temperature. My dear students, so whatever the area is below this, whatever the heat actually supplied, and the area under this should also be same. Let this be Tm. And I will write this as, look at what is the entropy change. It is S2, it is S3. So therefore, whatever the actual heat supply is taking place, so when I calculate the mean, for that also the heat transfer should be same. So what is the heat transfer on TS diagram? Area under the curve. So mean temperature is Tm. So now heat supply can also be written as Tm into, yes, Tm into, so this is S2, this is S3. So this area is Tm into delta S. This is delta S. This is S2, this is S3, and this area S2 minus S3. Exactly. Wonderful. So you know that when I am calculating a hypothetical temperature Tm, these two heats must be same. There is no problem in calculating H1. There is no problem. Already H1 is given in the problem. It is the enthalpy at the inlet to the turbine, and the inlet conditions to the turbine are 18 bar and 400 degrees centigrade. If you see 18 bar and 400 degrees, the enthalpy is 3165.54. So this is 3165.54, of course, kilojoule per kg, no problem. Now we need to calculate H4. My dear students, I have to calculate H4. How do I calculate? Where is that? H1 minus H4. बहुत अच्छा problem है sir ये. Now actually what I do is, generally pump work is very small. So I can neglect the pump work. If I neglect pump work, H3 and H4 are same. But in this problem, if you see clearly, the specific volume is also given. It means we are supposed to take the pump work also. चलो देखते हैं sir. So the pump work is given by minus VDP. ठीक है? And when nothing is given, I assume the process of pumping from 3 to 4 as isentropic. So therefore, minus VDP. This condenser pressure is given, this boiler pressure is given, I can easily calculate. So the specific volume is given. So what will be the specific volume? It is the specific volume because this is pumping. So this is nothing but, the specific volume is nothing but it is VF. VF at what temperature? Lower temperature, condenser pressure. So the VF is given into dP. What is dP? The pressure difference between boiler and condenser. So, but you should be very careful with units. Why, sir? Because these pressures are given in bar and enthalpies are given in kilojoule per kg. So, convert pressure into kilopascal. So, 1 bar is 100 kilopascal. So, this is 18 and this is 0.08. So, therefore, from here I can calculate pump work, VDP. So, the specific volume is also given. What is the specific volume? VF. The specific volume is given. Dekho, please, it is the liquid that is pumped. So therefore, VF is liquid specific volume is 0.001. So therefore, this VF is 0.001 into, and dP. What is dP? 18 bar, lekin convert in kilopascal. 1 bar is 100 kilopascal minus the condenser pressure is 0.08. Bar means 100 kilopascal. So this will give me the pump work. So already you know that pump work can also be written as H4 minus H3. If I apply steady flow energy equation, H4 minus H3. From here I get pump work. Let me see, I have calculated these values. Let me check. Yes, sir. And the pump work is, I have calculated this. But therefore, and this pump work, equate this to this. Already H3 is known. What is H3? H3 is equal to HF at lower pressure. So H3 is HF at lower pressure, that is 173.88. So this is known, 173.88, and this pump work is also known. And if I equate these two, I'll get the value of H4. Obviously, H4 should be greater than H3 because whenever the work input is given to the fluid, its enthalpy increases. So H4 is more. From here, I can easily calculate H4, and you get the value of H4 as 175.67 kilojoule per kg. Okay, now just observe what is H3, 173.88. What is this 175? This is almost, there is a difference of around 2 kilojoule per kg. Even if you neglect, it will not affect much in your answers. So I can easily write H4 also equal to H3 because pump work is very small. So heat supply can be written as H1 minus H4 or H1 minus H3. It doesn't make much difference, so don't worry at all. But anyway, I have shown you how to calculate. Now, look at carefully. Understand? So, pump work is negligible. Negligible and it is negative work. So, दोनों में negative ही ले लेना. मतलब value, you just take magnitude. H4 minus H3 is positive value and VDP is positive value because P2 minus P1, higher pressure minus lower pressure. Okay, when you equate, I get this value, 175. Once H4 is known, now there is no problem. Look at carefully. So heat supply is given by H1 minus H4 and that should be equal to Tm into S2 minus S3. Okay, so there is no problem with S3. What is S3? It is SF. It is on saturated liquid point, curve point. S3 is known to me. So good. It is at lower pressure, 0.08 pe SF. What is SF? 0.5926. So therefore, S3 can be written as SF at 0.08. It is 0.5926. Exactly. 0.5926. So I'll get this value. This is 0.5926 given in the table. But unfortunately, I don't know S2. But where is 0.2? It is in the wet region. So S2 is equal to SF plus X into Sg minus SF. But please note down that all these points are at lower pressure, that is 0.08. So this is Sg, this is SF, and we have to calculate S2. How do I calculate S2? So SF, already SF is known, 0.5926 plus X. The drainage fraction, he said moisture content should not exceed 15%. So what will be the drainage fraction? 85%. That is 0.85 into SG. What is SG, sir? What is SG? SG is given as 8 point, kahan pe? 8 point, let me check, sir. 8.287, exactly. 8.287, 8.287, and this is 0.5926. So if I calculate S2, let me check, sir. 0.5926, 0.85. So you will get S2 as 7.13284. S2 value is known. Now S3 is already known, S2 is known, Tm. But please note down that this is in Kelvin. Okay, so H1 is already known, given in the problem. H1 3165.54, 3165.54 minus H4. Just now we have seen what is H4. इधर देखना, H4 175.67, 175.67, 175.67. This is my heat supply. Tm into S1, S2 minus S3. Already S2 is 7.13284 minus S2 is known to me. S2 is this, S3 is 0.5926, and you will get the value of Tm. And if you calculate Tm, I think you are getting 457.38 Kelvin. But he's asking in degree centigrade, subtract 273. So you will get the answer as 184.38 degree centigrade. This is the mean temperature of heat addition. This is the mean temperature of heat addition. This is the mean temperature of heat addition. So this is a good question, sirs. Okay, chalo. No problem at all. Let me write clearly. Temperature in degree centigrade is 184. So the answer that you need to substitute here is, he's asking in degree centigrade, 184.38 degree centigrade. Chalo, let's go to the next question. Dekho, the atmospheric air at a dry bulb temperature of 20 degrees centigrade enters the heating coil. This is the heating coil. Air at 20 degrees centigrade is entering the coil, and the coil is maintained at 60 degrees centigrade, and the air after absorbing heat from the coil is leaving at 30 degrees centigrade. He is asking, what is the efficiency of the coil? Please note down that efficiency plus bypass factor is equal to 1. Efficiency, it shows what is the actual achieved during heating or cooling. So bypass factor shows what is lost. So bypass factor is a negative term. Okay, now you know, my dear students, what is efficiency? Actual gain in temperature by ideal gain. What is the ideal gain here? Ideally, it can gain from 20 to 60. See, actually the temperature of air is 20. Ideally, it should reach coil temperature. So ideally, what is the difference? It is 60 minus 20. That is, ideal gain is 60 minus 20. And what is the actual gain? The actually it is gaining from 20 to 30. So therefore 30 minus 20. So this is the actual gain by ideal gain, and this is 10. 30 minus 20 by this is 40, and I think you are getting this as 0.25. So the coil efficiency is 25%. So if in the same question he is asking bypass factor, you know that bypass factor is uncontacted factor, and already I have derived in my class efficiency plus bypass factor is equal to 1. But in the problem, bypass factor is not asked, so it will be 1 minus efficiency. So 1 minus 0.25, it is 75%. But this is not asked, just for revision I am telling you. Okay, chalo. Let's go to the next question. Read this question, a good question. Anji, read the question. A refrigerator operates between 1.24 bar and 13.6 bar. The lower pressure is 1.24, that is evaporator pressure, and the condenser pressure is 13.6. If the liquid is subcooled, there are two cycles. One is, my dear students, understand carefully. The first cycle is, Mitro, we'll take a line. The first cycle is this one. इससे काम नहीं चलेगा, हम यही ले लेंगे। हाँ, द फर्स्ट साइकिल इज दिस 1, 2, 3 and 4 dash. Very good. The first cycle is isentropic compression, constant pressure heat rejection, throttling, and constant pressure heat absorption. This is the first cycle. Later on, he said, if the liquid is subcooled 20 degree, this is 20 degree. So the new cycle is, there is another cycle, my dear friends. The another cycle is compression, then condensation, subcooling, then throttling, and then constant pressure heat absorption. So there are two cycles. He is asking the percentage increase in COP. Let us calculate before subcooling original case. So original COP calculate karenge without subcooling. What is the original case? Originally it's like this: compression, condensation, no subcooling, throttling. So original cycle is 1, 2, 3, 4 dash. I repeat, sirs, without subcooling, compression, condensation, throttling, and constant pressure heat absorption. 1, 2, 3, 4 dash is the original cycle. So now COP is nothing but refrigeration effect by work input for VC cycle. What is the refrigeration effect? For this cycle, it is H1 minus H4 dash. But 3 to 4 dash is throttling. So 4 dash can also be written as 3. So therefore, refrigeration effect is H1 minus H3. That is H1 minus H4 dash. But 4 dash and 3 are same, throttling hai. So therefore, H1 minus H4 dash, but 4 dash is 3. So by work input, what is the work input? H2 minus H1. Exactly. So let's calculate without subcooling the COP H1. Already H1 is given as 186.45 minus H3. What is H3? 90.26. Okay. By H2 minus H1. H2 is 240.55. 240.55 minus H1. What is H1? 186.45. So if I am calculating the COP without subcooling, I am getting the COP as kitna aa raha hai, sir? This is turning out to be 1.778. Now what he says is, with respect to the original cycle, what is the increase in COP if there is a subcooling by 20 degree? So now let us calculate new cycle COP. What is the COP, sir? Refrigeration effect. Now, my dear students, the new cycle is compression, condensation, subcooling, throttling. This is discontinuous line because irreversible. Don't think that it is a continuous line. Nah. So therefore, there is throttling, then constant pressure heat absorption. So heat absorption from the storage place is taking from 4 to 1. So what is the new refrigeration effect? It is H1 minus H4, right? So it is H1 minus H4 by work input is 2 minus 1, which is same. So let's calculate the COP in subcooled cycle. So H1 is already known. Where is H1? 186.45 minus H4. What is H4, sir? H4. देखो sir, H4 is also H3 dash because 3 dash to 4 is throttling. 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 So I will write H3 dash is H4. So already H3 dash is 78.66. 78.66 by H2. What is H2? 240.55 minus H1. What is H1? 186.45. Can you give me the value of second COP? So if I calculate the second COP, I'm getting this as 1.99242. 1.99242. So percentage increase changes always with respect to original. So percentage changes final COP minus original COP by original COP into 100. Already original COP is known, COP1 is known, COP2 is known, and by COP1. And if I put, I'm getting the answer as 12.06 percentage is the right answer. 12.06. You put these two values. COP2 is this 1.99242. COP1 is 1.778. By COP1 is 1.778. I think you are getting around 12.06. Okay. We'll move to the next question without wasting time. Read the question. A gas turbine with air as the working fluid. Please note down that the working fluid is air. Has an isentropic efficiency of 70%, that is 0.7, when operating at a pressure ratio of 4. I repeat, when the pressure ratio is 4, the isentropic efficiency is 70%. Now the pressure ratio is increased to 6. So originally the pressure ratio was 4. Now the pressure ratio is increased to 6. Okay. In both the above cases, inlet condition of the turbine and the specific work output from the turbine remains same. What is remaining same? With whatever the condition the fluid is entering the turbine, in either cases, in first case the pressure ratio is 4, in the second case the pressure ratio is 6. In both cases, the entry conditions to the turbine are same, and at the same time the work output from the turbine is also same. Then what is he asking? Assuming air as a perfect gas, ठीक है sir. What does perfect gas mean? The specific heats are not changing with respect to temperature. During expansion, temperature keeps on dropping, but over that range, the specific heat is assumed to be constant. ठीक है sir. Then the isentropic efficiency of the turbine for the pressure ratio 6 is, I repeat sirs, when the pressure ratio was 4, the isentropic efficiency was 70%. Now he is asking, if the pressure ratio is increased to 6, what is the new isentropic efficiency? My dear students, as you know, I taught in class, this isentropic efficiency is a function of pressure ratio. That's why, if you want that to be independent, we use polytropic efficiency. Right. Now observe. देखो, let us take the gas turbine cycle. ठीक है sir. This is the simple cycle. Isentropic compression, constant pressure heat supply, isentropic expansion, and then constant pressure heat ejection. ठीक है sir. Okay. Now, if you observe, the expansion is not isentropic. It is irreversible adiabatic. This is the actual expansion from the turbine because isentropic efficiency is given. So what is the turbine work? My dear students, can I write this as H3 minus H4? Yes. Where from you got this equation of turbine work as H3 minus H4? This gas turbine is an open system. For open system, if I apply steady flow energy equation and with some assumptions that kinetic potential energy changes are neglected, I'll get this equation. ठीक है sir. Now, my dear students, can I write this as Cp into T3 minus T4? Exactly, sirs. So, okay, this is the equation. Now, let's see what is isentropic efficiency of a turbine. So, I can write the isentropic efficiency as actual work by isentropic work. And Cp actual work is H3 minus H4. Isentropic work is H3 minus H4s. So, if I write H as Cpt, in the numerator and denominator, as it is a perfect gas, Cp will remain same. So from numerator and denominator, Cp gets cancelled. So you will write the efficiency as the isentropic efficiency of the turbine as T3 minus T4 by T3 minus T4s. Wonderful. So in this, I need T3 minus T4. So what is T3 minus T4? This can be written as turbine efficiency T3 minus T4s. Absolutely fine. Wait. So I'll do some important manipulations here. So let us take T3 common. So T3, why are you taking T3 common? Because in both the cases, he clearly said the inlet to the turbine is same. So T3 in both cases, it is same. So let's take T3 out. 1 minus T4s by T3. Okay. Now you know very well, 3 to 4s is a reversible adiabatic process. Moreover, the working fluid is an ideal gas. So I can apply T3 by T4s is equal to P3 by P4s power gamma minus 1 by gamma. My dear students, please do not apply this equation for 3 to 4 because 3 to 4 is not reversible. So to apply this equation, 3 conditions must be satisfied. The working fluid should be ideal gas, the process must be reversible and adiabatic. But please note down 3 to 4 is irreversible, so you cannot apply. So यहाँ से already you know 3 to 4. Pressure 3 to pressure 4 is the pressure ratio. This is the pressure ratio. This is Rp. So T3 by T4s is nothing but Rp power gamma minus 1 by gamma. So come to this equation. So T3 minus T4 can be written as T3 turbine efficiency, correct? T3 into 1 minus, now you have T4s by T3. So what is T4s by T3? Ulta. It will be 1 by Rp power gamma minus 1 by gamma. So I request everyone, if possible, remember this, because the turbine work is given by Cp into T3 minus T4. Cp into T3 minus T4. Cp into T3 minus T4. What is T3 minus T4? Turbine efficiency into T3 into 1 minus 1 by Rp power gamma minus 1 by gamma. This is the equation for turbine work. So what is that? Cp, turbine efficiency, T3. This is T3. 1 minus 1 by Rp power gamma minus 1 by gamma. So the turbine work can be written as Cp T3 turbine efficiency into 1 minus 1 by Rp power gamma minus 1 by gamma. This is the one. Very good. Now, clearly he said, my dear students, clearly he said the turbine work is same in both the cases. Point number one. Second point, the inlet conditions are same in both cases. Whatever may be the pressure ratio, in this problem he gave the inlet temperature is same. Okay. Now what I do is, as the turbine work is same in both the cases, so I write WT1, WT2. Therefore, CpT3 turbine efficiency 1 minus 1 by Rp power gamma minus 1 by gamma. This is the first case. This is the first turbine work. First case is equal to, second case is CpT3 turbine efficiency 1 minus 1 by Rp power gamma minus 1 by gamma in the second case. Clearly, T3 is same, because in both the cases the inlet temperature is same. Cp is constant. Don't cancel this. This is the first case isentropic efficiency. Now finally my equation becomes the isentropic efficiency in first case 1 minus 1 by the pressure ratio in first case gamma minus 1 by gamma is equal to the turbine efficiency in second case 1 minus 1 by Rp in second case gamma minus 1 by gamma. Very good. So what is the first isentropic efficiency? 70%, that is 0.7. And what is the first pressure ratio? It is 4 power. Gamma is 1.4 minus 1 by 1.4. So should be equal to the second efficiency, I don't know, into 1 minus 1 by the second pressure ratio is 6. 1.4 minus 1 by 1.4. So if I calculate from here, I'll get the turbine efficiency in second case, that is pressure ratio is 6. So answer is 0.5714. Please kindly you also check calculation part. Please kindly check calculation part whether I am right or wrong. So this is the answer, sir. Wonderful. Let's not waste time. We'll go to the next question. Now take this question. The specific humidity of atmospheric air at 30 degrees centigrade. The specific humidity is given as 0.15 kg of vapor per kg dry air. Omega is given, and the standard atmospheric pressure, the atmospheric pressure is given as, I write this as total pressure. Because why I write total pressure? Because in atmospheric air there is dry air, there is water vapor. So the total pressure is sum of the partial pressures. That's why I write atmospheric pressure as P total. It is 760 mm of mercury. Okay. The partial pressure of vapor, actually it is partial pressure of vapor, is in mm of mercury is, my dear students, there is no need for you to convert this pressure into Pascal or bar or kilopascal. I'll tell you the reason. The equation for omega is 0.622 PV upon P total minus PV. Excellent, sirs. My dear students, pressure can be written as rho GH. Already this is given in mm of mercury, and he is asking also PV in mm of mercury. So this is mm of mercury, this is also mm of mercury. Very good. So if you are converting into rho GH, Newton per meter square, P is equal to rho GH, P is equal to rho GH. तो क्या होगा? Rho G cancel होके फिर only heads will remain. So there is no need for you to convert directly. If this is in mm of mercury, this should also be in mm of mercury. So very simple. So now omega is already given as 0.15. It is a simple straightforward question. So 0.622 Partial pressure of vapor, I don't know. What is the total pressure? It is 760 and PV. And please note down that as this is in mm of Hg, these all will be in mm of Hg. And he's also asking in mm of Hg. So you will get the value of PV. Let me check. 17.89 if I am not wrong. 17.89 mm of Hg. Absolutely fine. Okay, right. Now, let's move to the next question without wasting time. Chaliye, take this question. Come on. In an ideal Brayton cycle, air from atmosphere at 1 atmospheric pressure and 300 Kelvin is compressed to 6 atmospheric pressure. ठीक है? No problem at all. No problem at all. Now, next is the maximum cycle temperature is 1100 by using a large air fuel ratio. ठीक है? If the heat supply is 100 megawatt, not milli, sorry, 100 megawatt. Which of the following? It is MSQ. So let's try to cover everything in a single question. ठीक है, sirs? Let me draw the cycle. Isentropic compression, constant pressure heat addition, isentropic expansion, constant pressure heat rejection. This is our Brayton cycle. Ideal बोला है, मतलब no isentropic efficiency, nothing directly. ठीक है, sirs? Now, P1 is given as 1 atm and T1 is given as 300 Kelvin. Okay, sirs. It is compressed to 6. So what is the pressure at 2? It is 6 atm. ठीक है? The maximum temperature, where is the temperature maximum? After the supply of heat, you are supplying. So here the temperature is maximum. And T3 is equal to 1100 Kelvin. ठीक है? The heat supply is 100 megawatt. Okay, no issues. Which of the following statement? The thermal efficiency of the cycle. As it is an ideal cycle, I think you must be knowing the equation of ideal Brayton cycle efficiency. 1 minus 1 by Rp power gamma minus 1 by gamma. If you do not know, you should remember this because examination is approaching. Now, so efficiency is 1 minus. So please note down that these questions are important from GATE, 𝐂𝐸, Thermodynamics, Applied part and ME Mechanical Engineering also. 1 minus 1 by, what is the pressure ratio? P2 by P1. P2 is 6, P1 is 1. So the pressure ratio Rp will be equal to P2 over P1. P2 is 6, P1 is 1. So it is 6. So 1 minus 1 by, air is the working fluid. 1.4 minus 1 by 1.4. You will get the efficiency. Let me check, sir. How much is this efficiency? I think you are getting this as 40%, that is 0.4. So please observe here, the thermal efficiency of the cycle is 40%. So option A is correct. Work ratio is 0.35. Back work ratio is 0.45. The power output is 40.15. Let us try to find out all this. So the first part is over. Now let me erase this, sir. Let me erase. So isko hata denge, sir. Let me erase. So this is my working area. Chaliye. Now, as I told you, the most important point when I was taking your plus classes, whenever you come across gas turbine cycle questions or gas refrigeration cycle questions, that is Bell-Coleman refrigeration cycle, the most important part is temperatures. Find out temperatures. Chalo, dekhte hai, sir. T1, T3 are known. And I have also told you, whenever it is an ideal cycle, in class I derived, product of even temperatures is equal to product of odd temperatures. This happens even in Otto cycle. So I can write this as T1, T3 is equal to T2, T4. Already I have given you so many times. Chalo. How do I calculate T2? If you see 1 to 2 process, it is reversible adiabatic compression. So T2 by T1, T2 by P1, gamma minus 1 by gamma. T2 by T1, 300. P2 by P1. What is P2 by P1? 6. Gamma is 1.4 minus 1 by 1.4. So यहाँ से I will get the value of T2. What is T2? What is the value of T2? It is 500.5 Kelvin. No problem at all. Now, T1, 300. T3, what is T3? 1100 is equal to T2. We have calculated it is 500.5 into T4. Everything is known except T4. Please give me the value of T4. It will be 659.27 Kelvin. Exactly. No problem at all. So once this is known, let's try to find out the mass flow rate, because the heat supplied, where is heat supply taking place? From 2 to 3. So if I apply steady flow energy equation, it will be H3 minus H2, but it is given in megawatt. So therefore, mass flow rate into, you have supplied from 2 to 3, so therefore H3 minus H2. And the working fluid is an ideal gas. Enthalpy can be written as CP/T. So CP is taken out, it will be T3 minus T2. One more thing. The specific heat is in kilojoule per kg per Kelvin. So you will get this value in kilowatt if this is in kg per second, but this is in megawatt. Units are not matching. So convert this into kilowatt. So 100 megawatt is 100 into 10 power 3. I'm writing here. My dear students, let me erase this. So now I'm writing 100 megawatt is 100 into 10 power 3 is equal to 100 megawatt. 100 is equal to m dot into Cp is 1.005 into T3 minus T2. What is T3? What is T3? It is 1100 minus T2. What is T2? What is T2? 500.5. What is the mass flow rate? ध्यान से सुनो. If this is in kilowatt, so it will be kg per second. And if you see, the value is 165.99 kg per second. What to do with this mass flow rate? Let me tell you very clearly. Once the mass flow rate is known, I can easily calculate the turbine work. How to calculate turbine work? The turbine power is equal to, the expansion is taking place from 3 to 4. So therefore, as it is taking place from, dhyan se suno sir. So let me calculate turbine work. So it is m dot into 3 minus 4, H3 minus H4. So power of the turbine can be written as m dot. What is H3? Cp T3 minus T4. So turbine power, what is m dot? M dot is 165.99 into 1.005 T3 minus T4. What is T3? T3 is 1100 minus T4 is 659.27. So therefore turbine power आपको मिल जाएगा. So you will get the turbine power as 73.52 kilowatt. This is the turbine power. This is the turbine power. The turbine power is 73.52 kilowatt. From this, I can easily calculate. So it is 165. Okay, fine. Where is that? 160. This is 659. Correct. Now, my dear students, we'll do one thing. Let's calculate the work ratio. We know that first efficiency can be written as net work by heat supply. The efficiency is already calculated as 0.4. Net work I do not know. By heat supply, already heat supply is 100 into 10 power 3 megawatt है. तो ये किलोवाट में आ रहा है सर? नहीं, एक सेकंड. This is also in, 1 second please. Oh, this is also in megawatt. I'm sorry. This is in megawatt. Let me check once. Let me calculate. So 165.99. Yes. This is megawatt. This is in megawatt. So therefore, this also in megawatt. So let's calculate in megawatt. So if I put this 100 in megawatt, अगर ये megawatt में है, this will also be in megawatt. So already actually from this equation you get it in kilowatt because the specific heat is kilojoule per kg per Kelvin. This will be in kilowatt. So divide with 1000, you get it in megawatt. Wonderful. So from here I get the net work. So this will be in megawatt. The net work is, if I calculate, my dear students, it will be 40 megawatt. Wonderful, sir. Once the net work is known, there is no problem in calculating the work ratio. Let us calculate the work ratio. ध्यान से सुनो. What is the work ratio? The work ratio is net work by positive work. Positive work is turbine work. So work ratio is net work. What is the net work? The net work is 40 and the turbine work is, the net work is 40 and the turbine work is, where is the turbine work? It is, both should be in same unit. Net work is 40 megawatt and the turbine is 73.52. Both are in megawatt. So if you are calculating work ratio, I am getting the work ratio as 0.544. The work ratio is 0.345. It is wrong. The efficiency of the cycle is 40%. It is correct. Back work ratio. Everyone knows work ratio plus back work ratio is equal to 1. So back work ratio is 1 minus work ratio. So back work ratio is 1 minus. The work ratio is 0.544. So from here you get back work ratio as 0.455. Yes, it is correct. Back work ratio is correct. Wonderful, sir. The power output is 40. Net power output from the turbine. Yes, the power output, net power output is, suno carefully, 40 kilowatt diya. Galat. It is 40.1 megawatt. The net power is 40 megawatt, but this is given in kilowatt. So this, had it been megawatt, देखो ये बहुत इंपॉर्टेंट है सर यूनिट. हैड इट बीन मेगावाट दिस वुड हैव बीन करेक्ट, बट इट इज गिवन इन किलोवाट. ये गलत है. सो ऑप्शंस ए एंड सी आर करेक्ट. आई रिक्वेस्ट एवरीवन टू गो थ्रू यूनिट्स प्रॉपरली. वेरी गुड. नाउ प्लीज रीड द नेक्स्ट क्वेश्चन. रीड द नेक्स्ट क्वेश्चन. रीड द नेक्स्ट क्वेश्चन. Come on, come on. Come on, come on. Read the question. Moist air at, this is a good question, 105 kilopascal, 30 degree. So, relativity flows over a cooling coil in an insulated air conditioning duct. Saturated air exits the duct, but you should be very careful. The inlet total pressure is 105. The exit total pressure is 100 kilopascal. In this question, this is very important observation. So let me show you very clearly. There is, क्या है sir? Cooling coil. This is the cooling coil. Air is entering at 1 and air is leaving at 2. ठीक है. So what is the pressure given here? The total pressure given here is 105 kilopascal. Let me write it as 1. And the temperature given here is 30 degrees centigrade. And the relative humidity here is 80%, that is 0.8. ठीक है sir. And the exit pressure is 100 kilopascal. And the exit temperature is 15 degrees centigrade. But please note down that क्या बोला है वो? Saturated air exits. So therefore, what is the relative humidity here? Saturated air is exiting. So 100%, which is nothing but 1 because saturated air is leaving. Okay. The saturation pressure of water, the saturation pressure of water, that is PVS, at 30 and 15 degree R. So here PVS is given here at 30 degree. At 30 degree, the saturation pressure is 4.24 kilopascal. And at 15 degree, this is 15 degree. So here PVS is given. So let me write it as 1. and here it is given as 1.7 kilopascal. ठीक है sir? हाँ, and the molecular weight of air water is given as 18 gram per mole or 18 kilogram per kilomole, and this is 29, sir, 28.94, and that of air is 28.94, and moisture removed is, but it should be in gram of vapor per kg dryer. Be careful. So very simple, sir. It is a cooling and dehumidifying coil. So air with some moisture content is entering. So it is undergoing dehumidification and some moisture is removed. And you have some humidity here. The difference of these two omega will give me what? Moisture removed. Chalo, ek kaam karte hai, sir. Let us calculate omega at section 1. It is 0.622 PV by P total minus PV, but this should be at section 1. But note down carefully, section 1 total pressure is different, section 2 total pressure is different. Chalo, let's calculate omega 1. 0.622. Unfortunately, I don't know PV, but PVS is known. So relative humidity is equal to PV by PVS. So it is 1 to 1 pe. PVS is known. Okay, what is the relative humidity given? 80. So 0.8 is equal to PV1 by PVS1. What is PVS1? 4.24. I repeat, sirs. So here phi is equal to PV by PVS 4.24. From here I can calculate PV. If I calculate PV, let me check, sir. If I calculate PV, it is 3.392. So here I am getting PV as 3.392. Put karo yahan pe 0.622 PV 3.392 by P total. First P total is 105 minus 3.392. So if I calculate omega here, the first omega I am getting it as yahan ka omega. I am getting this omega as 0.02076 kg vapor per kg dryer. Now come here. Phi is equal to PV by PVS. Here the relative humidity is 100%. Phi is 1. When phi is 1, PV and PVS are same. So PV is equal to PVS. So ये आ रहा है 1.7, sir. So let's calculate omega 2. It is 0.622 by P total minus PV. So omega 2 is equal to 0.622 by P total. What is P total, sir? The P total at second is, dekho, 100 minus 0.622 PV by P total minus PV. What is PV, sir? 1.7. PV is 1.7 because whenever it is saturated, phi is 1. When phi is 1, PV and PVS are same. So PV is 1.7. P total minus PV. So yahan se I will get the value of omega 2, and that omega 2 is 0.01756, I think, if I am not wrong. 0.0. एक बार कैलकुलेट करेंगे सर, into 100 minus 1.7. 0.010756. 0.010756. This is kg vapor per kg dryer. And this is the moisture at second state. This is the moisture at first state. So how much moisture is removed? For 1 kg dryer, this minus this, take the difference. So omega 1 minus omega 2 is the moisture removed. So if I calculate the moisture removed, omega 1 minus omega 2, my dear students, if I calculate, I am getting the difference as, if I calculate the difference, I am getting the value as 0. Omega 1 0.02076 minus 0.010756. I am getting the answer as 0.010008 kg vapor per kg dryer. But please note down that denominator is same per kg dryer, but he is asking gram of vapor. So kg can be written as 1000 gram. So if I multiply with 1000, this will be 10 gram of vapor per kg of dryer, because he is asking in gram. So therefore the answer is 10, 10, 10. Very good, sirs. Wonderful. Now let's take this question. It's a good question. Read the question. Read the question. Let's complete this question. I don't have value. I think I have to calculate. Let me check. Come on. A refrigerating machine uses freon as a working fluid. The temperature of the refrigerant in the evaporator is -10. The condensing temperature is 40. The cooling load, that is refrigeration load, is 150. And the volumetric efficiency of the compressor is 80%. The compressor speed is 720 RPM. The displacement volume in meter cube, but it is given as 10 power minus 5. चलो कैसे करेंगे सर? बहुत सिंपल है सर. And you know very well, the volumetric efficiency I have already derived in classes, in regular classes. It can be written as m dot into specific volume at the inlet to the compressor by pi by 4 d square ln k. I have already given this in class. I have derived in class all this, where k is number of cylinders or number of compressors, and here nothing is said, so I'll take this as 1. So k is 1, no problem at all. Now, this portion can be written as swept volume. देखो. So the volumetric efficiency can be written as m dot V1 by actual volume entering the compressor to the swept volume. So this can be written as Vs into N. But you should be careful with units. If m dot is in kg per second into meter cube per kg, kg per second into meter cube per kg, this will be meter cube per second. This should also be in meter cube per second. So swept volume is meter cube, but this is in RPM. Divide with 60, you get meter cube per second. So no problem at all. Dekho. But unfortunately, V1 is known, sir. What is V1? Dekho. If you see the cycle of VC, vapor compression refrigeration system, 1, 2, 3, 4. At what point the fluid is entering the compressor? Point 1. Point 1 means it is the lower temperature. So at lower temperature, at this is the entry point. So lower temperature, vapor specific volume is V1. Lower temperature, specific volume of vapor, it is 0.08. Lower temperature. So specific volume is let me write here. The V1 is 0.08 meter cube per kg. Actually, it is meter cube per kg. No problem at all. Because this is -10 and the higher temperature is 40. So entry is occurring at at -10 degrees centigrade. So therefore it is 0.08. No problem at all. So volumetric efficiency is given as 80%. Where is that 80? कहाँ पे है sir? Somewhere it is given, I think. कहाँ पे दिया रे? कहीं पे? Yes, 80%. This is given. V1 is known. He is asking swept volume. Speed is given. Volumetric efficiency is given. Unfortunately, I don't know mass flow rate. ध्यान से सुनो sir. Let's keep mass flow rate in kg per second. This will also be in RPM को RPS कर लेंगे. So units will match. How to find out m dot? Very simple, sir. The refrigeration capacity or the cooling load is equal to m dot into refrigeration effect. What is the refrigeration effect? The fluid is absorbing, the refrigerant is absorbing heat from 4 to 1. So it is H1 minus H4. But what is H4? 3 to 4 is throttling. So H4 and H3 enthalpy remains same in throttling. So H4 can be written as H3. ठीक है सर. देखो, what is RC? 150 watt. But be careful, यहाँ पे problem हो सकता है सर. These enthalpies are in kilojoule per kg. So kg per second into kilojoule per kg. So it will be kilojoule per second. This will be in kilowatt. Because enthalpies are in kilojoule per kg. This should also be in kilowatt, but it is given in watt. पहले इसको kilowatt में convert करना. 0.15 is m dot into units match होने के लिए kilo. H1 is how much? What is H1? Minus 10 degrees centigrade vapor enthalpy. Minus 10 degrees centigrade vapor enthalpy. Minus 10 degrees centigrade vapor enthalpy. Hg is 183. H3. What is H3? 40 degrees centigrade liquid, saturated liquid HF. 40 degree HF. 74.5. I have not calculated. Let me calculate. So it is 0.15 divided by 183 minus 74.5. This will be, mass flow rate will be 1.3825 into 10 power minus 3 kg per second. So now everything is known. Let us substitute here. My dear students, let's substitute here. Units are very important. Volumetric efficiency in this equation. The volumetric efficiency is 80%, so 0.8. M dot we have calculated 1.3825 into 10 ki power minus 3 into V1. What is V1? 0.08 divided by Vs into speed. Speed is 720 galar. It is RPM. This is kg per. Dekho, this is kg per second. So divide with 60. So you will get Vs as. Let me calculate, sir. 1.3825. ठीक है, into 0.08 into 60 divided by 0.8. So I'm getting this as Vs ka value as 1.152 into 10 power minus 5 meter cube. Already 10 power minus 5 is given. So answer will be 1.152. Answer is 1.152. It is the correct answer, 1.152. Let's check. ठीक है सर. हाँ. Come on. Read the question. In a gas turbine plant working on Brayton cycle with a regenerator of 75% effectiveness, the air at the inlet to the compressor is 0.1 megapascal and 30 degrees centigrade. The pressure ratio is 6 and the maximum cycle temperature is 900 degrees centigrade. ठीक है. The percentage increase in the cycle efficiency due to regeneration. So let me draw the cycle. He has not given any isentropic efficiency. So let us assume a simple cycle. Isentropic compression, constant pressure heat supply 1 to 2, 2 to 3, 3 to 4 and 4 to 1. ठीक है सर, बहुत बढ़िया. Now, there is a regenerator used, sir, and please note down carefully. The inlet pressure is given as 0.1 megapascal and the inlet temperature is given as 30 degrees centigrade. 273 plus 30 is 303 Kelvin. The pressure ratio is given to us as 6 and the maximum temperature in the cycle is 900. So add 273. I think कितना आ रहा है सर? 1173. Am I right? चेक करते हैं सर एक बार. 900 plus 273. Okay. और क्या है सर? The percentage increase in efficiency. Let us calculate the efficiency without regeneration. It's a simple cycle. For a simple cycle, the efficiency is given by without regeneration, original. So 1 minus 1 by Rp power gamma minus 1 by gamma. This is the equation for the efficiency of simple Brayton cycle. So let us calculate the efficiency. 1 minus 1 by Rp, 6 power gamma is 1.4 minus 1 by 1.4. Let's see what's the value. So 6 power 0.4 divided by 1.4. So I am getting this as 0.4. So without regenerator, I am getting the efficiency as 40%. Let us see with regenerator what will be the efficiency. My dear students, the fluid is leaving the turbine at 4 and will allow this fluid to enter a counterflow heat exchanger and will allow to heat the fluid coming from the compressor. Let 2A be the process taking place in the counterflow heat exchanger and the fluid is losing heat. The fluid which is coming from the turbine is losing heat from 4 to B and the fluid which is coming from compressor is gaining. ठीक है sir. Now ideally, what is the difference between turbine exit and compressor exit? It is 4 and 2. So ideal difference is T4 minus T2. Actually, how much it is gaining? 2 से लेकर A तक. So can I write the effectiveness of regenerator as actual gain by ideal gain? So Cp is same. So I'll in terms of enthalpy I write. Later on I'll divide with Cp. So you get Ta minus T2 by ideal gain by actual gain. The actual gain is from 2 to A, TA minus T2. Ideal is from 4 to 2. So T4 minus T2. Unfortunately, none of the temperatures are known to me. But I know very well, I can easily calculate T2. 1 to 2 is, so without regenerator, the efficiency is 40%, note down. Without regenerator, the efficiency is 40%. Please note down that. ठीक है sir. Now, let's calculate with regenerator. आराम से. 1 to 2 is reversible adiabatic compression. T2 by T1 is equal to Rp power gamma minus 1 by gamma. So T2 by T1, what is T1? 303 is Rp. What is Rp? 6. Gamma is 1.4 minus 1 is 0.4 by gamma minus 1 by gamma. So let's calculate the value of T2. So 6 power 0.4 by 1.4 into 303. So it is 505.5 Kelvin. T2 आ गया. So therefore T2 is known. Now T3 is already given, highest temperature. I think I can calculate T4 easily. How? Product of even temperatures T2 T4 is equal to T1 T3. This is an ideal gas turbine cycle. T2 is 505.5 and T4 is, I do not know, is equal to T1. What is T1, sirs? 303 into T3 is 1173. So let's try to calculate. So 303 into 1173 calculation में कुछ गड़बड़ हो सकता है सर, थोड़ा टॉलरेट करो. T1 T3, T1 is 303, T3 is 1173. Okay, T1 T3 311 is equal to T2 T4. T2 is 505 T4. Let me check. 303 into 1173 divided by 505.5. 703.1. Okay, sir. Now, let's calculate, my dear students, this value. Already the effectiveness is given as 0.75, 75%. Okay, I don't know TA minus T2. What is T2? कहाँ पे है सर? T2, 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 505.5. By T4, T4 is 703.1 minus T2 is 505.5. This 505. 505.5. ठीक है, let's calculate TA. 0.75 into. You should also calculate. Don't depend on me, please. Plus. I'm getting TA as 653.7 Kelvin. TA 653. T2 कितना है? T2 is 505. Okay, ठीक है. Now, what is the efficiency with regenerator? Net work by heat supply. Now we are not supplying heat from 2 to 3. So 2 to A is in regenerator and A to 3 is actual supply. So let me write the efficiency equation. So if I write the efficiency equation, so it will be turbine work minus compressor work will be net work. So in numerator, net work is T3 minus T4 is turbine work minus compressor work is T2 minus T1 by heat supply, network by heat supply. Supply is taking place from A to 3, so H3 minus HA. That is CP निकाल दिए, तो we have removed, sirs. We have removed. So ये इसको neatly लिखेंगे, sirs. We'll write so neatly. So therefore, second case regenerator efficiency is turbine is 3 minus T4 minus T2 minus T1 by T3 minus TA. I repeat, turbine work minus compressor is net work, heat supply is A to 3. So all temperatures are known. Let me substitute. T3 is 1173 minus T4 is 703.1 minus T2. Where is T2? 505.5 plus T1. Where is T1? It is 303. Okay. divided by T3 minus TA. T3 is 1173 minus TA is 653.7. And we are getting this efficiency as 0.515. So he is asking percentage increase in efficiency with respect to actual. Actual is 40%, new efficiency is 51.5%. So therefore, increase in efficiency is equal to the new efficiency minus old efficiency with respect to old you are calculating into 100. So the new efficiency is 0.5149 minus old efficiency is 40% by the old efficiency is 40% into 100. So this will be minus 0.4 into 100. So we are getting around 28.7% increase in efficiency due to regenerator. Always you note down that regenerator always improves efficiency. Okay, let's take the last question for today. Take this question. Last question for today. So can you see? दिख रहा है sir? Can you see? चलो देखते हैं सर. Actually this cycle should be, इसको zoom भी नहीं कर सकते सर. क्या दिख रहा है सर आपको? Cannot see. ठीक है, मैं इसको अरेंज करवाता हूँ. Somehow it's a good question. तो I'll arrange की थोड़ा फिगर बिग करके नेक्स्ट सेशन में लेता हूँ. So thank you my dear students. I'll come with some more questions. Thank you. God bless you. And this video is helpful both from XC and mechanical engineering point of view. Thank you. Good night.